Material Science, Chapter 6, Phase Transformation. This is the final chapter of which is in part B. Previously, we already covered in part A. So in part B, we will have Gibbs phase rules and construction of phase diagram. In the Gibbs phase rules, basically this is the represent of criteria for the number of phases that will coexist within the system at equilibrium. It is expressed by a simple equation, which is P plus F equals C to C plus N, where P is equal to number of phases present, which is phases solid, liquid, and solid plus liquid. Okay, and then for F is equal to the number of degrees of freedom, which is number of externally controlled variables such as temperature, pressure, composition. So we will have the number. So the number, it will represent the degree of freedom in terms of temperature, pressure, and composition. And then we have C equal to number of components in the system. And also finally we have N, which is non-compositional variable, which is temperature, pressure. So for example, let me see for the binary temperature composition phase diagram, which is for example of copper and silver. So the pressure is constant. Basically, when we talk about binary temperature composition, the parameter for the temperature varies, and also for the composition. But for the pressure, it keep constant at 1 atm. For the solution, for in term of finding the variable of P plus F equal to C plus N. So in term of parameter involved, we have the non-compositional variable, which is N is equal to 1. Okay, for the temperature. And then we have a component for C is we have two component, which is copper and silver, which is indicate for 2. And then we have phases present, whereby we have P is equal to 1, which is considered single phase field, whereby include of alpha, beta, and liquid L region. So it will indicate only single phase field. So the P is equal to 1. So we have this information so that we can find the value of F. So once we substitute the value, so we get the value of F equal to 2. So the number of external control variable is 2. So the parameter are composition and temperature. So basically, in this case, if one of the parameter, which is given P, C, and N, so it required us to get the value of F, or given F and not P, so we will need to get the value of P. So this is a basic formula, or simple formula, indicates the 4 parameter involved. If we have two phases coexist, let's say we have alpha liquid, beta liquid, and combination of alpha plus beta phase region, which is we have the uh, P is equal to 2. So that means we can get the value of F is equal to 1. So in this case, we have the value of external control variable is equal to 1. Okay. So this is the table show the parameter change of in single phase. Okay, in single phase here, and also we have two phases coexist, which is these two phases, and also we have three phases present. So which is we have the value of P varies from single phase we have 1, two phases we have 2, three phases we have 3. So that if we have this value, so we substitute the value and we get the value of F. So in this case we have the value of single phase, we have F equal to 2, meaning of we have parameter composition and temperature, which means we have composition and number 1 and temperature is 2. There is 2, F equal to 2. And for in this case we have F equal to 1, whether we have the composition or temperature. Okay, so we don't know whether this composition or temperature. Okay, we need necessary to specify from these two. Okay, and then we have in three phases, basically we have the F equal to 0. So the composition of all three phases and temperature are fixed. So that's mean composition, temperature, and the value of uh, pressure is all are fixed. Okay, so we don't know. So we already know that they are all fixed. So this is the way how to calculate the parameters involved, which is 4 parameters here by using the Gibbs phase rules. Okay, in the phase diagram later on we will see the uh, binary phase diagram. So in the binary phase diagram also we have a different category of phase diagram, which is different type, which is eutectic phase diagram and peritectic phase diagram. After this we will see different in term of phase diagram, and we make some analysis in term of the existing of parameters by using the Gibbs phase rule, and also we will use the microstructure. We discuss on microstructure if the temperature varies or composition varies, so that we will need to determine the microstructure exists in terms of liquid, solid, and liquid solid. And also we need to determine the amount of phases in terms of how many percent. This one we will use lever rules to identify the amount of phases. This one we already covered in the previous parts, which is part A. So basically from the previous slide, we already covered the Gibbs phase rule, whereby we have three phases present. So in this case, the example of the phase diagram, which is copper silver phase diagram, but basically when we substitute the value and then we determine the F is equal to 0 for the three phases present, and then it will indicate or meaning that the composition of all three phases and temperature are fixed. Basically, this condition mean for a eutectic system, but in this case of F equal to 0, uh, I already mentioned that in a binary phase diagram we have the several type. So in this case, if f are equal to 0, so it will meet for the eutectic system, whereby we have the diagram indicates the diagram is something like this, whereby we have the liquid and also we have the solid solution. So at this area, when we increase the temperature or decrease the temperature at the certain amount of Ag percentage, the solid solution, it will 100% transform to be a liquid. Okay, if we compare to this, it will transform to be alpha plus L first, and then also go to the liquid. So if we have this line, also we have beta plus L, and also transform to liquid. But in this case, at 0.71.9% of Ag, so the solid solution will transform to liquid, okay, at this point. So this point we will call it the eutectic system. Okay. So for the development of microstructure, basically when we talk about the microstructure, let's try to consider the copper nickel system. Okay. Uh, so in this case, we have the composition of copper and also nickel, uh, and then the composition will be produce alloy in composition. Let's see, we look at the 35 weight percent of nickel, uh, and also we look at the 65% of weight percent of copper. As is cool slowly from the 1300 degrees Celsius. Here is the phase diagram of copper nickel phase diagram. So in this case, in order to look at the what will happen at the microstructure of the copper nickel composition, we will draw one line of composition start from 35 weight percent of nickel, okay, and all the way project, okay, and will intersect with the uh, this line, okay, and also intersect with this line. So at point A, okay, we will start to look at the microstructure changes from the higher temperature and start to cool down, and we will see what happened to the microstructure produced. So at A, we have the at 1300 degrees Celsius, basically the alloy is completely in liquid phase. So at this, the composition is basically we have liquid L is 35 weight percent of nickel, and we have 65 weight percent of copper. To cool down, it will go to B, whereby B is a intersection line of the liquidus. Okay, at this area, this point when we project in terms of temperature, it is we can get the value of temperature is around here. So at this temperature is about 1260 degrees Celsius. It will intersect at the liquidus line, and at this line we have the solid uh, start to form, okay, whereby a solid we said alpha start to begin to form, and the composition of alpha is basically 46, Okay, how to get 46 value of alpha. Basically, we can project the line, okay, up to this hit the intersection line at the solidus. So and then we make a projection to the x value, and this value is around 46%. So the composition of alpha, we will get 46% weight percent of nickel, and the rest is 54% weight percent of copper. So note, basically we will state in term of alpha 46 nickel. Okay, so we will understand that this composition is basically telling the composition of nickel and copper. Okay, and then at this point we have the 35% nickel in liquid. Okay, here, so there are two phases in alpha and alpha here, and also we have liquid here. So we will state the value of alpha 36 nickel, and then we have 35 liquid in nickel. So we have fraction of alpha, we will increase. Okay, so the schematic diagram of this composition, basically we can write something like this, where start the nucleation takes place of alpha, okay, at 46% nickel. So and then the rest is we have the liquid composition. Okay, when the temperature is lower down at the region of alpha and liquid, whereby we put the symbol as C, and we can see that we draw a line. Okay, so that from here and from here it will intersect at the liquidus and solidus line. So here we can identify the value of alpha alpha here 43 nickel, and also the liquid we have 32 nickel, whereby we project this line down to the intersect the axis here. So we will get the value of the 32 nickel. And the microstructure we can see a little bit bigger. The alpha start to bigger and bigger. The nucleation takes place, and the bigger microstructure, so that we can draw is something like this. What happen when we the temperature start to cooling down at D, whereby the intersection takes place at D. We have the solidification complete at around 1220 degrees Celsius, whereby we have also two point of intersection, whereby we have the alpha and also L liquid. So for the alpha we have 35 nickel. For the liquid we need to make a projection from here until here. So the value is around 24 nickel. And then for the intersection line at D, we have the bigger microstructure of alpha, and whereby it start to have a grain boundary, okay, bigger and bigger. And finally we have at E, whereby the position of E is in the area of alpha, so that upon crossing solidus line, the remaining liquid completely solidified. So if we can see the only alpha, okay, so that the value of alpha is 35 nickel polycrystalline solid solution, so that we can draw the microstructure is completely the grain boundary. There is no liquid exists in this diagram. So this is the way how we complete draw the schematic diagram from the various position, whereby we look at the fixed composition, and we look at the temperature different, which is we start to decrease the temperature, or we cool the temperature slowly. So and then we produce the schematic diagram is something like this. In this case, we use a copper nickel system or phase diagram. Other binary phase diagram we can also do. Okay, so that in this case we can choose any composition. Let's say we want to choose at 45 nickel or 30 nickel. So basically is quite the same, but maybe at the certain temperature level is different. Uh, but in this case it's not quite interesting. But if we talk more on a different phase diagram, maybe quite interesting in terms of the uh, solidus line and liquidus line varies. Okay, after this we will see a difference of the phase diagram when we talk about the microstructure different. Okay, for another binary phase diagram, basically if we look at the tin lead tin system phase diagram, and also we have the copper zinc phase diagram. Two type basically the this kind of phase diagram we call it two type of solder. Okay, solder to basically use in the common electrical soldering or permanent bond between metal workpiece. So in this case, we have the combination of lead and tin, and also we have copper and zinc, which is for the lead and tin system. We call it a soft solder. Yes, basically we use this kind of solder material to make a bonding between wires. Okay, and then we have another one, we call it hard solder, which is copper zinc system, but basically the term we call it brass. Okay, this brass basically used in the other application, which is for decoration, for the appearance of, because of this kind of gold like appearance, for the knob, drawer, pulls and door knob, and also it used for low friction and corrosion resistant for the locks, hinge, gears, bearing, casing, zipper, plumbing, hose, coupling, and a lot of electrical plugs and socket. So this is the like I already mentioned before, when we want to look at the different phase diagram of in this case we have lead tin phase diagram and copper zinc phase diagram. It show a different condition of liquid solution, uh, solid solution of alpha beta in different composition. So in this case, if we want to look at the certain composition of copper zinc at 40 zinc composition, maybe it will very interesting to look at from its microstructure. So so we will we will go for the eutectic phase diagram. Eutectic we call it binary eutectic phase diagram, which is the composition of lead uh, SN phase diagram, which is something like this. So in this case, this is a simple phase diagram of binary eutectic phase diagram. So basically, this phase diagram we call it binary eutectic. This is due to the we have a three single phase diagram, which is alpha, beta, and liquid. whereby we have alpha here, and also we have beta, and we have the liquid at the upper region. And also there are two phase diagram exist. We have alpha plus liquid in this area, and also we have beta plus liquid in this area, and another one at the below here we have the alpha plus beta. So this is the binary eutectic phase diagram, consists of these phases. Okay, for the alpha phase, we consider as a pure lead. Okay, in here there is a 100% pure lead, and then solid solution risk in lead basically, and then the tin as a solid composition. Okay, here we can see the composition. Basically, the boundary line is here and also here. So in this composition, we can see the limit here is whereby the 19.2, whereby the alpha composition here. And then for the beta phase, which is in this area, okay, in this area. So basically consider as pure tin, solid solution rich in tin basically, and then lead as a solute, okay, lead as a solute in this tin. For the line, basically we have the liquidous line, whereby consists of AE and EF in red color line. And then for the solidus, basically we have the line of AB, okay, AB, and then FG, and then BEG. Okay, this we call it a solidus line. And we have a solvers line, which is BC here, and then we have GH. Okay, solvers line. So there is a new term from instead of liquidus, solidus, and we have a solvers line. Okay, the boundary between alpha and alpha plus beta, and also boundary between beta and alpha plus beta. So let's discuss on the microstructure. Okay, in terms of lead-tin phase diagram, or we call it binary eutectic phase diagram. So at the solubility limit of alpha phase, basically we have the maximum solubility of Sn. Okay, in this point, the maximum of solubility of Sn here, the maximum we will go at this at a temperature of 183. This line temperature 183 here, and the slope of BC basically solubility of Sn in Pb. Okay, this line, and decrease with temperature. So the maximum is 183, the maximum composition, which is 19.2, and the Sn value is decreased slowly when the temperature is decreased. Maybe we can project at this point, maybe we project here, maybe less at 5% maybe, and then Sn become less soluble in Pb. Okay, so in other words, is less soluble. And for the case of solubility limit of beta phase in here, in basically we have the point here, heat at the 183 degrees Celsius, the maximum of PB. In this point, the maximum of PB solubility is 97.5. Okay, at this GH line, we have the solubility of PB in SN decrease with temperature, and also we call it the PB become less soluble in SN. Okay, during in this line. So the horizontal line BEG, basically this line BEG indicates the temperature at 183 degrees Celsius. This indicate that lowest temperature liquid phase may exist. Okay, liquid phase may exist. The liquid is around here and is in the lowest. Okay, lowest. And at this point, maybe the highest liquid exists, but the lowest is this area. Melting temperature of PB and SN at PB, this line basically we have the PB is lower by the SN addition, the temperature decrease along the line, the liquidus line of AE. Okay, this line. And then for the SN is lowered by the PB addition, the temperature decrease along this FE line. So for the liquidus line AE and FE, basically we call it the eutectic point at E. Okay, so we call it eutectic point. Okay, and then for this eutectic point, basically the reaction whereby the transformation from liquid to the liquid area, and then finally transform to the alpha plus beta phase that can be represented using this kind of reaction, whereby from the liquid phases, when it start to cooling down, it will produce we will transform to alpha solid solution plus beta solid solution, whereby there is no transformation to beta liquid or alpha liquid in this region. It just transform from liquid, start to cool down, and finally uh, produce or transform to alpha and beta in solid solution. Or in another way around, we have when we start to heat this composition, whereby we have 61.9 composition of tin. We heat or we increase the temperature, and this line it will transform to liquid. Okay, by using this reaction. And then if we want to talk about the microstructure difference or changes, maybe we can start at C, and then we start to cool down, or we lower the temperature from the at 300 degrees Celsius. So at J, we can discuss on the totally liquid. At the composition of we state that at C4, whereby the C4 is consists of 40, okay, 40 weight percent of tin. So at this condition at J point, basically the weight percent of tin is 40. Okay, and it is totally liquid when cross liquidus line. When it hit the liquidus line here, nucleus of alpha phase begin to form. Okay, and then it will cross to the point K. So we can discuss on the alpha phase continue to grow, keep much bigger, and we can see the alpha composition and liquid composition takes place there. So at here we can determine the composition of alpha and liquid by using the cross-sectional line. We make the intersection here, and also intersection here. So in terms of alpha, we will get the value here from the projection downward until here, and at this point we will make a projection of liquid, okay, until here. So we will get the composition alpha and liquid here. At point L, whereby in this case in the phase of alpha liquid, so and here we have just above a little bit of 183 degrees Celsius, whereby this temperature we call it this the 183 degrees Celsius is a eutectic temperature, and then the composition of alpha is basically in at 19.2 okay, weight percent of SN, and also the composition of liquid is basically we make a projection until here is basically 61.9. Okay, so we can discuss on the microstructure is much bigger. Okay, start to be bigger of the alpha, and also the liquid is start to decrease if compared to this value. Okay, and the microstructure basically, and we look at the point M. In this case at point M, just below a little bit at 183 degrees Celsius, whereby the composition of phase we have the alpha plus eutectic structure. We call it here is a structure, we call it eutectic structure, whereby the composition of we can draw the schematic diagram is something like this. Okay, and the red blue line is something like we call it eutectic structure, and the stripe taking place where the microstructure produced, whereby we have the value of beta basically from the value from the projection of line here until this line, okay, whereby we have 97.5, so we put here. So in this case of the eutectic alpha, basically the value is 19.2 we can get from this point. Okay, just make one line little bit below this line, basically it will hit this line, this point, and this point. Okay, but we take the value of this. Okay, actually the value is a little bit in this case a little bit higher, maybe 97.6 or something, or in this case maybe lower at this point maybe lower 19.1 or something, but we just put the value because of the boundary level. So the eutectic alpha is basically the present in eutectic structure, the value is 19.2. And then we have the microstructure at lead tin alloy primary alpha. Basically in the real picture or taken from the scanning electron microscope, basically we can see from this diagram, whereby we have the circular bigger in dark color is basically the alpha, and also we can see from the like zebra stripe, we can see is the dark color and light color. For dark color is basically for the primary alpha here, and for the light color is basically from the beta. Okay, so this is how we project. If we compare to others phase diagram, this uh, eutectic phase diagram, we have a different existing of like a zebra stripe color, shape color. So let's see from the different composition, whereby we have the line of composition of 61.9. At this line, we will see the eutectic at the different the feed composition at a different temperature. So solidification takes place at uh, just the state as a C3, and at point H, maybe we can explain at the liquid composition of 91.6% weight percent of tin, and is totally liquid. And at point I, okay, and below a little bit of the eutectic temperature, basically a liquid transform to be a phase, alpha phase and beta phase here. And the composition of alpha is basically 19.2 of Sn, and also the beta composition, that is 7.5. If you compare from the previous slide, which is at this 40 line, we can see the composition of below the eutectic temperature, and also below in this line is different. Okay, whereby here the microstructure consists of the primary alpha here. Okay, whereby we have the bigger uh, alpha consists in the schematic diagram. Okay, microstructure alternate layer of alpha and beta, whereby we can see a lamella. Okay, and the microstructure in this point, basically, if we look at the real image of a scanning electron microscope, uh, it will produce something like this. Okay, there is no bigger primary alpha exists. Okay, whereby the alpha phase is darker layer, and the beta phase is light layer. So another picture or discussion related to the binary eutectic phase diagram. Okay, we can actually we have a three region. Okay, at the boundary at this eutectic, we call it eutectic composition, whereby we have a 61.9. Here we call it eutectic, whereby the composition is something like this produced in this region, whereby the boundary from the eutectic to this area, whereby we call it the hypoeutectic. So in this region, we can see alpha is very primary, okay, whereby the lamella, okay, also produce. But in this case, the higher composition of Sn, basically we can see the existing of primary tin, okay, produced here, and also the same of the lamella produced. Here we call it the hyper eutectic. Okay, in this case, we can compare with the different region uh, and the microstructure produced. Okay, let's see from the different composition at C1. Maybe the composition at C1 is below than 5, maybe 2 or 3 composition of a tin. So here we can see at point A, point B, and point C. whereby at point A we have totally 100% of the liquid, and at point B is a heat at the liquidus line and also solidus line. Okay, the microstructure can be represented is something like this. And at point C, whereby the solidus across the solidus line, and we can have the alpha is 100%. Okay, and it will produce the microstructure is something like this. So at line C2, okay, maybe we can represent is something like this. Okay, and if we want to see the transformation of alpha, okay, here is no alpha exists, and then the alpha from here is start to transform and bigger, and then it will hit at this area, uh, whereby the alpha is almost 100% start to form and something like this. And when hit to this line, it will start to form another beta. Here we can see a beta stripe here. Okay, it will produce. Okay, and finally we will cover a perithetic phase diagram, which is phase diagram, whereby we will discuss category of perithetic in the PTAG phase diagram. Okay, and you can see that there is a different line of solidus, liquidus, solvus line. So in this case, we call it binary perithetic alloy system or binary perithetic phase diagram, whereby the perithetic we have the line of basically represent in this point. Okay, perithetic. So we will see a difference of microstructure if compared to perithetic. And in this case, we have the melting temperature of both components are quite different. Okay, perithetic, there is a transformation of perithetic from the this line, alpha liquid, and then heat this perithetic temperature at 118 C. And from there, it will start to, there is a intersection of line of beta also, and also line of alpha plus beta, also line beta liquid, and also alpha liquid here. So there is a very interesting point here to discuss. We call it perithetic phase diagram. So the transformation, we have two phases interact at fixed temperature. Two phases interact at fixed temperature here, 118 C, and then it will produce a new phase. Okay, from here to this phase, and then this phase, and also this phase. And a peri means around. That means the original solid phase becomes surrounded or coated by the new phase. If we can see from the alpha liquid in this area, okay, basically the form is something like this. And then when it hit this area, this point, to become beta, okay, this is the line of beta also, it will transform is something like this, completely from alpha and become beta, whereby the beta is start to surrounded, okay, of the alpha, and finally the alpha will vanish and become beta. Okay, at this point we call it perithetic transformation, or for the case of temperature, we call it perithetic temperature here. And then the reaction taking place where the liquid phase react with a solid phase to form a new different solid phase. Okay, actually there is a solid of alpha, and then finally it will produce a solid phase of beta. Whereby the composition of this happen at the composition of 42.4 of Ag. Okay, we can also look what will happen to the microstructure when we want to discuss at this line, maybe at 24% Ag. And also we can discuss at this point, 42.4. And also we can discuss as this 55% Ag here, what will happen to the microstructure. So when we want to discuss at 42.4, okay, we have several points here. Okay, the first one is at this point. So basically there is a line region of liquid. So we have the liquid region 100%. And then when it start to cross, the process of alpha start to nucleate and then hit this point, whereby we have the phases of alpha and liquid here. The value of alpha composition and liquid composition can be determined at this line 7 and 55, and it's also happened to the beta at this point, whereby at this point beta 100% transform. Okay, and if we have another line here, maybe we can also discuss what will happen to this point. Basically this point is a liquid and beta region, whereby the composition is something like this. The value can be determined, the beta value and composition and liquid composition can be determined by make this line and hit this 48 and 77 line. So and then we put the value here. So in this case we have a line alloy 1, so which is we have the composition of 42.4. So we will discuss on the 3 point, which is we have this for 1400 degrees Celsius line, and also we have a point whereby the higher temperature, okay, we have 1186 plus delta T, maybe a little bit higher, and also a little bit lower at this 1186 minus delta T, maybe a little bit lower here. So what will happen? Previously, we already discussed on the microstructure and also the composition of alpha, composition of liquid, beta, and in this slide we will discuss on the amount of a phase, which is we will use lever rules to discuss on the this situation. So in this case of this point, whereby we have a point at 1400 degrees Celsius, and we will make this line, and then we have the intersection of this point and this point. For the case of alpha, okay, alpha point here, alpha phase, the amount of composition we can calculate at 26%, whereby we get from the value of 55, okay, minus 42, and then divide by the whole from here to here, okay, and then we get 26. And for the liquid phase composition amount, we have the value from 42.4 minus 7 and divide when the whole from 55 to 7, and we get the value of 74%. And for the composition of liquid phase, basically we will get from this point, the intersection of liquidus point, which is 45% Ag. And for the alpha phase, we will get the composition at 7% here. 7% of Ag here. And it also happened to the 1186 degrees Celsius plus delta T, maybe a little bit higher. So the intersection line basically at this point and this point, okay, whereby the amount of alpha and liquid phase, basically we will get from this value of, for the alpha phase we have 43%, whereby we have the value of 66.3 minus this value, which is 42.4, and divide by the whole from here to here. Okay, and also for the liquid, we have from here minus here and divide by the whole from here to here, and we get 57%. As you can see from the lower point here, which is basically we don't have alpha, so that basically the whole thing is basically at the beta only, okay, whereby the line is from the beta line here, okay, up to this line. So it is 100% beta. So in this case, we can see that the transformation from the alpha basically at 26% and become higher, and finally is vanished due to the peritectic transformation, and finally it will produce a beta at 100%. And for the liquid, is basically start to reduce, okay, as the alpha is increased, something like this. Okay, maybe we can look at the different point. So at line of 25 Ag in this red line, basically we will also discuss on the 3 point, which is at 1350 degree Celsius here, and also the line is the point where the a little bit higher 1186 and lower, a little bit lower at 1186. So at 1350 degrees Celsius, we have the point here, whereby we need to have the line, which is the cross section between this point and this point, whereby the alpha value is 5 if we project, okay, here. And then for the for the liquid, this is from here, okay, maybe higher is this not for 55, basically maybe higher, okay, maybe around 60, okay, because this line, this is a mistake, typo error, okay. We make a line here, and then it will cross something here, and then to determine the value, we need to make a projection cross intersect with the x axis here, maybe 62, 63, okay, here. And we calculate for the amount of phase in percent. For the alpha phase, we have this value, okay, around 60%, and for the liquid phase we have 40%. At 1185, okay, we have a little bit higher, okay, at this point and also at this point. Maybe we can take this point 63.3 66.3 and we have the 105. So we just put the number here and we start to produce the value. Okay, and it's also for the 1185 below here. So at this area, the I think this is wrong. Okay, this area which is the 100% beta produce. Okay, it's not here, wrong. Okay, and then we start to calculate the amount of phase in percentage. Basically the same as the previous slide. Also, we can get the condition of amount composition at this line 55% Ag, and also we can also try to look at the 60 Ag, what will happen. Okay, basically for the determining the amount of phase and composition, basically we will use the lever rules, and what will happen to another other line. Okay, so maybe you can try do by yourself to identify the value. Okay, in this case, what happened to the for the exercise? What happened to the phase equilibrium of PBSN alloy in terms of the specific temperature selected at A, B, C, D, and E? What is the phase alpha beta in terms of composition and amount of phase? Okay, maybe you try by yourself to get the value. And that's all, I think. So try to, after this, I will give a assignment related to this. And also maybe you need to compile, make a summary of the what is going on the part A and part B. Okay, maybe you need to do a mind mapping, the same as the previous chapter. Okay, thank you. Bye bye.